Wow, packed house, right? How great was that keynote? Sahir's an awesome speaker, and in fact, mentioned Atlas Search. So you're here for a little bit of deep dive into that. You're super lucky today because Partho Bardhan from Chicago, in Chicago, he's the local guy, is here to teach you some tips and tricks for using Atlas Search. So let's get started.
Right. Hey everyone, Partho Bardhan. I work with many of our community users and enterprise customers based out of the Midwest. So thank you all for joining us today. Packed houses, awesome. Just give me a thumbs up. I don't have the headphones, so I don't know if there's too loud or not. All right, thank you. Love this. Awesome. So today we're going to be talking about some tips and tricks of using Atlas for a very compelling customer experience search kind of a use case. So I really want to start by talking about this cool app that I built, right? And what it does is it allows you to search for movie names, right? And it's pretty easy. Like I take my IDs and I search for it. It's great. But my UX friend tells me that it's not the best of experience and can be better. I don't get why my friend says so, because all I need to do is take the ID, search for the ID in a text box, and it shows me the name of the movie. Ghostbusters is what I'm searching for. Should be easy, eh? I get it, right? You're smiling already. So the IDs are probably harder to remember. So yeah, I'm sure like my friend's right, and we can improve this. So that's what we are going to build today on. It's going to be an iterative approach to improving an app. We'll start with what is like a query and how can you improve from a direct query, like an equality-based query, to a syntactic-based search. We'll look at how you can improve the search experience with things like scoring, and then how you highlight those search results, how you sort them. We'll look at how to easily create recommendation engines of what people are searching versus what they could also look at. We'll also look at type ahead kind of experiences such as autocompletes, faceted search for more granular search, and then we'll go into what everyone's talking about, right? So things like vector search, semantic-based search, so really like meaning-based search than just comparing syntaxes, okay? All right, so what I'll do is I'll use a search engine to improve the UX that my friend said hasn't been that great. So, I mean, I took a system class once, and I know in order to put together this, there's a database that you need, there's a search engine that we need, and then we need like some kind of query to hydrate the search engine. The search engine could be a Lucene, like could be an Elastic, Solar, Algolia, many out there. But this query hydrates that search engine, and then as new records come out, Hollywood releases a new movie, I send CDC updates to the search index. But hey, like along with keeping that search thing going, I need to keep in mind that what if something falls out of sync, so need an out of sync monitor, and then this search index is critical, need a backup system. There's also a different system, so need to learn an application language by developers. And then once I've done all of this, I get to now build an application for my database and the application for search. That just turned out more complex than I initially thought, no? And that's where my friend says, hey, haven't you heard of Atlas Search? I was like, all right, what's cool about it? My friend says there's like 5 clicks. 5 clicks you need to create a search there. What does that look like? We go to where the collection is, where the data is stored, and in the collection, click on a search, like search index in there, click on it, and put a name to it. Here we're going to name it default, and then we are going to select the default configurations for that search, and that's it. In like 5 clicks, we just deployed a fully managed Lucene index. So Lucene, many of you are familiar, is the most popular open source search project out there. So we built all of that. And what all did we accomplish by doing that? So first, we compressed the database and the search index and all the synchronization between them in one. So I avoided the synchronization tags. Whoever was, let's say, a data engineer building these pipelines, ops or admin teams putting all of these together, they could now be like, all right, fine, one single command or a few clicks, that whole thing is avoided. For application developers, we don't have to learn 2 separate technologies now. We can use a familiar MongoDB query language in the familiar drivers of our choice, C# or Java, Python, whichever you prefer, Node, And finally, like you get the benefits of a fully managed platform, right? So things like uptime, redundancy of data, performance, security, all of those baked into the platform. All right, so we did, awesome. So we now get these benefits, but we just created a pretty simplistic, in 5 clicks, an index. How do I search it? How do I test it? Atlas UI in Search UI has a search tester, which allows you to pretty quickly see what index you have created and how it performs. I key in the term. I can even look at the underlying query for it, and pretty easily look at, OK, as I keep building, I can see what's going on, right? Pretty nifty that way. And what does it look like under the hood now? So the first thing is the index definition, right? So you have a couple of keywords there, mappings, and what it says, dynamic. So mappings is what maps like the fields in your records to search index records, and dynamic true says that index everything, right? So if you have like a 2 field, great. If you have 2,000 fields, everything, right? And that's what dynamic true does. The aggregation query is the one that uses that index and allows you to query through that index. Aggregation query builds on a popular framework in MongoDB called Aggregation Framework. Many of you might be familiar. What it does is allows you to create sophisticated queries using very simple stages. One such stage is called the $search stage. And here what I'm doing is saying, do a text search using the query called Ghostbusters in the path title or plot. And then I can take this and put it in the application driver of my choice. Here it's C#, and I just build this code. All of this is easily exportable from the client tools too, so you don't have to go and write everything if you don't want. OK, great. So I think I improved on my first version, and now I don't have to search with IDs anymore. I can just search with the name that I want, search with Ghostbusters, show me all the results. But it's interesting, if you spotted, like there was a third result here, Frighteners. That doesn't sound very Ghostbusters-like, but we'll see why that is. And my UX friend, a perfectionist, points out that we should do better and tried searching for Fighting Club, like the movie about didn't show up Fight Club. I thought that's what it would do, did not. Other things like why was that extra Frighteners record out there? And then, OK, we are sorting by relevance. What could we sort by something else, like year instead? Now, in order to understand why the Fighting Club didn't work, let's take an example of a phrase, the quick brown fox jumped over the lazy dog. And initially, if you all recall, like the mapping that we did in the index called dynamic true and mappings dynamic true, what it did was it took a default analyzer called Lucene Standard. What it does is it breaks down this phrase into smaller words, and it breaks it down into quick, brown fox, and so forth. And notice that it did not take the as a word in that because it's not important, right? It only takes the important words, but it did not take things like, it does not understand native English kind of searches or language spoken and written language kind of searches. So for that, an optimization you can do is change that analyzer from Lucene Standard to Lucene English. So what that does is it understands typically written English words. So jump for jumped, lazy and lazy with an I are kind of similar for laziness. Same thing for fight and fighting. All right, so that's a change that we need to do. Great. So we also discussed, like scoring. How did the sort order, how is that determined? The core of that in search or any relevance-based search technologies you might be familiar are called search scores. This is what gives relevance-based search their special thing. And if any of you are like interested in how that gets computed, it's a pretty nice mathematical formula around that. There's a lot of Wikipedia and like papers out there. It's called term frequency and inverse document frequency. A very simplistic way of putting that is like it's a handy algorithm to tell you how important a specific word or search term is in the corpus of your record set. Okay, so like fight, where you have 2 fights and you're searching for fight, it shows up. Then Fight Club, that has a specific score. So that's how it gets computed. All right, so I think like I'm becoming more of a search expert now. This is great. Can you hit play on this, please? Okay, so now that we learned how to put together like the query, we'll just see how this gets built out in how you can easily build this out. This is called Compass's aggregation builder. Pretty easily build out these search queries through like some drag and drops and some coding. Here I'm defining the name of the index. I'm saying which query path I'm using and what value I'm using to search for. And on the right, it'll show me preview of all the results as I build this, right? I'm also going to add a couple more fields to this called highlights, and I'm going to define what path there is. Hold on to what highlights is. We'll come to that shortly. But I define highlights, and then I go to the next stage where I project what fields I want to show in the output. I don't want everything. If I have 2,000 fields, I probably want 5 of them. And again, on the right, it'll show me a preview as the data goes through the code that I'm building. In the project stage, I also had 2 specific meta fields, the score field that we just discussed with the TF-IDF thing, and then a highlights field as another meta field. Again, we'll talk about highlights shortly. So once I've defined all of these, the preview shows, and I can pretty easily then go to this stage called an export pipeline, and I can export the whole query to either a C# or a Node or any other driver that I want, and it gives me the whole query in the syntax with all the included libraries and everything. All I need to do is just copy and paste it in my application code, right? So really making it easy as you start building some sophisticated queries out there. All right, so we learned a few new tricks now. So the way we refine the index, the initial mapping, map dynamic true index that we built, we're going to refine that, and we're going to add an analyzer and a search analyzer to my index. We're going to change it from Lucene.standard to Lucene.english. We are going to add, oops, sorry, this is building out here. Okay, we're going to add the analyzers. We're going to change from dynamic true to specific fields such as title and full plot as the fields that I want, and I'm going to call them string because that's a data type for them. And any sortable fields I'm going to add to that index definition. In the aggregation query, I'm going to use the search stage, and now I'm going to define the path where those fields are to query. I'm also going to call on the specific index name. Remember, we use the default index, not anymore. I'm going to call the actual index name that I'm going to search on. And finally, those meta fields, those don't get automatically returned. So I'm going to use the project stage to return the 2 fields called search score and the highlights field to show what's going on. All right, so we've been saying the word highlighting a few times. What is that? Essentially, what this does is it's a meta field that points out where and what field you're searching is present in the body of the record that's being returned. And the way this comes out in the result set is as like an array with a few records called values and type. The values here is the 5 years after the first movie of type text. Ghostbusters is of type hit, and more text after that. So this makes it really easy for you to put it on the UI by only finding out which of these in the result set are of type hits, right? And you can just highlight them in your UI and make it a pretty nice user experience for the fields that's searching. We also saw how we are doing search based on score. So if year was a field that you included in your search criteria, you could even use that to search outside of score. By the way, look at the score at the bottom. It'll load again. But if you look at the score, that's basically the relevance of the TF-IDF term that we're talking about. But now this also explains. You see, like ghost busting and Ghostbusters. This is what explains why Frighteners was showing up. Okay, awesome. So a few pitfalls to keep in mind. So things like it's very tempting in the aggregation framework in MongoDB that you can combine, operators from. Like there are 200 operators, you can just combine them together to get the experience you want. While that works, but sometimes you got to keep in mind the performance of it. An example is the search and sort stage. If you put them one after the other, what the sort stage does is it opens a cursor, asks all the search results to be pulled into memory, and then in-memory sort. So that's like slow, right? Instead, prefer to use the fields that you want to search on in your search index, and then use a score to sort that. The default analyzer, if you prefer a different language, use that. There are lots of, like, say, English, Spanish, Hindi, whichever you prefer, like you have spoken and written language analyzers there, so you can use that. And finally, if you want to present why the search is how it is, highlights and search operators are pretty useful for that. Okay, so we did a pretty good job in the second iteration, but my UX friend says, this is good, but I want to also provide recommendations. How do I go about doing that? So Atlas Search provides a pretty useful operator here called more like this. What it does is you pass a specific source document to the method. In this case, we are passing the name of the movie, Ghostbusters, Ghostbusters 2, whichever, and it returns what other movies are like it. So that's like classic recommendation engine right there, right? And implementation of this is pretty straightforward, where it's a single line of code. There's a C# code, again, can be in any application language that you like. It's a more like this operator, pass the source record, and it gives you what other records look like this, right? So pretty easily with a single command, we just put together a recommendation engine. Great, I love it. My UX friend doesn't. Says that, hey, this is good, but when people are searching, they like to have a type. They don't want to type a full term or a full phrase. It's pretty long. It's time consuming. Give me a way to show those results as they're typing. So many of you might call it type ahead. And in Atlas, sorry, could you go back one slide, please? Thank you. So this is called autocomplete. Atlas provides a pretty useful way of doing this. And what it does is, as you're typing for a few characters here, it shows up in the result set, and you can use that to provide a pretty compelling search experience in the UI. A really compelling thing about this is how fast this gets returned. So really, as someone is typing, what you want is in like milliseconds, right? I type, I see the thing right there, right? I don't want to wait even a second to hit tab. So this is what it does really well. And how do I implement this in code? For the index definition, remember up until now we had changed that mappings, like dynamic true to specific field names. You can add more fields in that search index. So we are going to, in addition to the individual fields of type string, we are going to also add and say title and plot, full plot. You guys are also going to be autocomplete. And in the aggregation queries, we're going to now keep calling that index with a name, not the default index. And instead of just a regular single query, we are going to do a compound query. And in that compound query, we'll have two should clauses. Think of it like, like an and kind of a clause. And in there, we're going to define that, hey, this field title should also match autocomplete, and this field called full plot should also be autocomplete. That's it, right? So that's how I iterate my query using the autocomplete operator. The documentation for these are very readily available on our docs page, and I can also discuss in more details if you're interested in these things. But it's important to, as you build these, some key tips of using this, right? One, we talked about that mappings dynamic true. Why not use that and instead use specific fields? Look at the difference in index sizes between the two. There's the first one that says dynamic. I'm not sure if you can see at the back, but at the top it says dynamic, and it uses some 37 megabytes when it's all the fields. When I simply use 3 fields, it goes down to 16 megabytes. I save 60% of my memory and storage, which is in turn like resource cost savings, right? The other thing to keep in mind is autocomplete. I added it in the third row. I have autocomplete on 5 fields. That increased my index size from 16 megabyte to 300. So this is something to be very, be cautious about. That autocompletes do require a lot of space. So only use autocompletes for the fields that you really need type ahead on. Don't use it for everything else, right? Keep in mind about min-grams, which is how many characters one has to type to see that autocomplete. Just using one character before you show autocomplete results may not be as beneficial to your user. Also is costly for your indexes. Maybe use it for 3 fields or 5 fields, after which you show the autocomplete results. Finally, just to reiterate, don't use search and sort stages separately. Combine them in the index and in the query. If you must use sort on other fields, there's a specific utility called stored source. Look at that. That allows you to sort and match on other fields too. Okay, so version 4 looking good. I like it, but my friend says that we need to let users refine the results better, give them more granular ways to search. And Atlas Search offers a pretty useful way of doing this through facets. And you can combine them in pretty complex ways. I'm going to show a more simplistic one. Input facets dynamically shows facets of what someone is searching on. Here I'm searching on movies, and automatically genres and cast show up as facets. And I can then allow users to narrow down the search. In this case, I'm going to select things like Bill Murray as the cast that I want, and it's only Ghostbusters, no more the other movie. Okay, perfect. So I've helped my users narrow down on how they search. How do I implement this? The index definition, if you remember, we are using strings and then autocompletes. You now get to use a third option on those fields called title and full plot called string facet. So the same field is being used in so many different ways. That's very useful. When I define string facets, what I'm doing is I'm extracting metadata of those fields to be used in the facets. And because I'm using metadata now, I'm not going to be using the $search for showing those facets. I'm going to be using a different tool, different operator called search meta. What this does is it takes just the metadata of those result sets and makes it different facets and then presents it on the screen. Right? And then I'm going to include that search meta in my query, and I'm going to show those genres and cast as separate facets. Okay? So this is great. I created a better experience, but then my UX friend says that, hey, all of this is good, but given what everyone's asking for, we need to have some semantic vector search in that. Otherwise, no one's asking for just regular searches. Meaning-based searches is what everyone wants now. So Atlas provides a pretty useful feature for that we might have heard downstairs at the keynote. Call it vector search, right? Now, before I go into vector search and semantic searching, let me just quickly explain what is semantic similarity. Semantic similarity means we represent an entity or a phrase or a body of text, anything, in vectors. And what are vectors? In mathematics, that's like something that has a floating point magnitude and a direction, right? And there are lots of Hugging Face, LangChain, Llama Index. You might have heard of many of these. What they do really well is create these high dimensional space of vectors. So, and very simplistically put, here we are only looking at 2 dimensions for cheese and pizza and different kinds of cheese. So what we are doing is like cheese is being represented in 2 dimensions, and it says that cheese maybe is a milk product, and cheese is related to mozzarella, cheese is related to pizza. Same way, pizza is related the same way. While this is very rudimentary, in real world you're looking at 1,000 dimensions, 1,500, 2,000 dimensions, lots of them, right? And that's what is used to determine similarity between 2 specific entities. Now, you take these dimensions, and you can use any inference API out there that's good for the Hugging Face has lots of, it's open source and has lots of useful libraries around that. The cloud providers have their own, so you could use any of them. And good thing with Mongo is we support arrays, right? Any body of text, in this case we have content, you take that and you put those embeddings in an array. And these embeddings come from your preference of vector generation libraries and toolings out there. And how you implement this in code is in the index definition. Remember the mappings and dynamic true we're doing? In the fields, we add the content embedding with a specific operator called KNN vector. The KNN vector is designed to capture vectors from popular vector generation models, and you can define how many dimensions you want to store it in. And define it put it in the KNN vector field. On the flip side, when you're searching for the data, there is another operator called KNN beta, which allows you to take the field that you're searching on, define the vector embeddings for that, and you compare the two. Keep in mind the search, whichever library you use for generating the vectors and for the results, the data set, and the vectors that you use to, and the vectors that you generate for the query set, the model generating those have to be the same, right? But once you generate those two vectors, Atlas Search has the algorithm to be able to compare them properly and then give you the search result. How does that look in implementation? I'm searching for capture poltergeist in a city. And if you look at the body, there's no mention of the word poltergeist, but it relates to ghosts and how they're caught in a city. This also shows when you click on that array field, all the embeddings that we generated, but this is a very clear way of showing how you can compare these vector embeddings together, like vector embeddings in your code. Okay, so now I can really say that I built a cool app. So I just want so to summarize, as we come to close, we talked about how we took a very simple, equality-based application, enhanced that with a search engine. We added things like autocomplete on that. We added relevance-based searching, fuzziness, sorting on that. We also looked at things like vector search and semantic search on top of that, along with doing granular searches with facets. So with that, I come to the close for this talk. I'm going to be around for a few more minutes. So please, if there are any questions, happy to discuss in the audience, or you can come up. And we appreciate any feedback. So the QR code is for that. Thank you for attending this talk today.